The cosmos holds secrets far stranger than fiction. Deep within its silent expanse, glittering star clusters act as cosmic laboratories, revealing truths that defy our understanding of physics itself. By the end of this journey, you will have explored 50 of the most bizarre discoveries ever made about these stellar families. We will uncover pulsars that cannibalize their neighbors and planets born in gravitational chaos. What is the true nature of the universe's most crowded stellar neighborhoods? Our journey into the bizarre begins with a cosmic horror story unfolding in a densely packed globular cluster. Astronomers discovered a pulsar, a rapidly spinning neutron star, engaged in a deadly dance with a nearby star. This system earned the terrifying nickname the Black Widow. The pulsar bombards its smaller companion with intense beams of radiation and powerful particles, effectively cooking it from a distance. This relentless assault strips away the companion star's outer layers, slowly vaporizing it into a cloud of superheated gas. The process is a form of cosmic cannibalism, where the pulsar feeds on the material being torn from its partner. This violent interaction generates some of the most intense gamma-ray emissions ever detected in such a system. Scientists first pieced this puzzle together by observing rhythmic changes in the pulsar's radio signals, which revealed the presence of a distorted, dying star orbiting it every few hours. Visualize a lighthouse on a distant shore, but instead of a gentle beam, it emits a sizzling, destructive wind that systematically dismantles a neighboring island. The companion star is stretched into a teardrop shape, its stolen mass spiraling toward the pulsar in a final cosmic embrace. This discovery revealed that even within the beautiful glitter of a star cluster, true monsters can lurk. The destructive dance of the Black Widow pulsar reveals a universe of extremes, but the strangeness does not end there. From stellar cannibals, we turn to cosmic survivors, planets that defy all odds. For decades, astronomers believed the dense cores of globular clusters were the last places you would ever find a stable planetary system. The gravitational pull from thousands of neighboring stars constantly tugs at any forming worlds, creating a chaotic environment where planets should be ripped apart or flung into the void. Yet they exist. One of the most famous examples is a world known as PSRB 1626b. This planet is a true ancient, over 12 billion years old, and it orbits not one, but two dead stars, a pulsar and a white dwarf. Its very existence is a paradox. How could a planet form or survive in such a violent stellar graveyard? The leading theory suggests this world was not born in its current location. It may have originally belonged to a single, sun-like star that was later captured by the dense binary system. Through a gravitational ballet of near misses and cosmic exchanges, the planet was stolen, finding a new home around the stellar corpses. Another possibility is that it is a second-generation planet, forming from the heavy element, rich debris of dead stars, a world born from the ashes of its predecessors. Think of it as a lone house, miraculously still standing in the center of a constantly shifting, collapsing city. The discovery of such worlds forces us to rewrite the rules of planetary formation and survival, proving that even in the most hostile neighborhoods, life, in the form of a planet, finds a way to cling on. These celestial survivors are not the only rule breakers in the old neighborhoods of space. Some stars seem to have discovered a cosmic fountain of youth. In ancient globular clusters, where all the stars were born at roughly the same time billions of years ago, astronomers find a puzzling sight. Scattered among the cool, aging red giants are hot, blue stars that should have burned out eons ago. They are known as blue stragglers, and their very existence is a direct challenge to our understanding of how stars live and die. A star's color and temperature are tied directly to its mass and age. Massive, hot, blue stars burn through their fuel in a cosmic blaze of glory, dying young. In a cluster where every star is ancient, every blue star should have vanished long ago. Yet here they are, shining with a youthful vigor they have no right to possess. So how do these old stars masquerade as young ones? The secret seems to lie in stellar rejuvenation. One leading theory points to violent cosmic collisions. In the densely packed core of a globular cluster, stars can swing too close to one another. A direct merger between two older, lower mass stars could create a single, more massive star. This new blended star would have a fresh supply of hydrogen fuel and would shine hotter and bluer, effectively resetting its evolutionary clock. Imagine two aging cars, each with broken parts, crashing and fusing into a single, sleek, high-performance vehicle. That is the chaotic birth of one type of blue straggler. Another, more patient method involves a binary system. Two stars orbit each other closely. Over time, one star expands as it ages, and its outer layers are gravitationally siphoned off by its companion. This mass transfer dumps fresh hydrogen onto the smaller star, causing it to gain mass, heat up, and turn blue, while the donor star is stripped down to its core. It is a stellar vampirism, a slow theft of life that creates a youthful-looking anomaly. These blue stragglers are not just oddities. They are evidence of the dynamic, often violent social lives of stars within these crowded clusters, showing us that even in the serene night sky, stars can cheat death itself. The cosmic youth of blue stragglers is not the only secret hidden within ancient clusters. Some of these stellar cities hold a far more massive and mysterious truth at their very core. Astronomers gazing at the colossal star cluster Omega Centauri have uncovered evidence of something that should not be possible: a double heart. This cluster, a vast swarm of millions of stars, appears to harbor not one, but two intermediate mass black holes, locked in a slow gravitational dance at its center. The first clue came from studying the motions of stars near the core. Just as you might deduce the presence of a large, unseen object in a dark room by watching how other objects are pulled toward it, scientists tracked the velocities of countless stars. They expected to find a single, dense concentration of mass, a single gravitational anchor. Instead, they found two distinct centers of stellar motion, 2 points where stars were whipping around at incredible speeds, each suggesting the presence of a separate, incredibly dense object. These are not the supermassive black holes found in galactic centers, nor the stellar mass black holes from collapsed stars. They are intermediate mass black holes, a long theorized but elusive class, with masses equivalent to thousands of suns. Their presence in one cluster is a profound puzzle. How could two such monsters come to coexist in the same stellar neighborhood? One compelling theory suggests that Omega Centauri is not a true globular cluster at all, but the stripped core of a dwarf galaxy that was devoured by our own Milky Way long ago. In this scenario, each black hole could have been the central anchor of its own original, smaller galaxy. When the two galaxies merged, their black holes sank to the shared center, forever bound together. Another possibility is that a single, larger black hole was disrupted, its gravitational hold shattered by a violent event, somehow splitting its influence. The implications are staggering, forcing us to reconsider the very definition of a star cluster and the violent histories that can forge these cosmic structures. The mystery of multiple hearts in a cluster is rivaled only by the enigma of stars that simply do not belong. We have already met the blue stragglers, old stars masquerading as young. But an even broader paradox exists. In the ancient realm of globular clusters, where every star was thought to have ignited in a single primordial burst over 12 billion years ago, astronomers are finding entire populations of stars that look suspiciously youthful. These are not just a few rebellious individuals, but whole groups of stars that appear billions of years younger than their cluster siblings. How can an entire neighborhood of young stars exist in a city that finished construction when the universe itself was in its infancy? The standard model of cluster formation is clear. A vast cloud of gas collapses, giving birth to a magnificent, glittering family of stars all at once. The ferocious stellar winds from the most massive of these newborn stars should then blow away all the remaining gas, shutting down the factory forever. No gas means no new stars. The cluster should then age uniformly, a fossil from the early cosmos. Yet the chemical fingerprints of these anomalous stars tell a different story. They show a different mix of elements, suggesting they formed from gas that was enriched by the previous generation. This points to a startling possibility. Some globular clusters did not have a single brief period of star formation. Instead, they experienced extended or even multiple episodes, separated by long pauses. Imagine a ghost town, silent for eons, suddenly roaring back to life with new construction, its workshops firing up again to forge a new generation from salvaged materials. The question is, what could restart a star-forming engine after hundreds of millions of years? One theory involves a slow, cosmic rain, perhaps residual gas or gas captured from a passing intergalactic cloud, slowly accumulated back in the cluster's core over vast timescales, eventually reaching a density high enough to trigger a second wave of stellar births. Another, more violent idea points to collisions with other clusters or gas-rich dwarf galaxies, a dramatic event that could funnel fresh fuel into the dormant system. This discovery shatters the simple picture of globular clusters as static relics. They are not just fossils, they are living histories, with chapters of their story written far more recently than we ever believed possible. The idea of ancient clusters birthing new stars is not the only way our view of them has been shattered. Some of these glittering swarms are not native to our galaxy at all. They are cosmic immigrants, the last surviving remnants of galaxies that our own Milky Way consumed long ago. These are the lost sibling clusters, and they serve as permanent fossils of our galaxy's violent, cannibalistic past. One of the most famous examples is the spectacular cluster known as Messier 54. For a long time, it was catalogued as just another brilliant globular cluster orbiting the core of the Milky Way. But detailed observations revealed a shocking truth. Messier 54 is not orbiting our galaxy's center. It is, in fact, the core of a separate, smaller galaxy called the Sagittarius Dwarf Elliptical Galaxy, which is currently in the process of being torn apart and absorbed by the Milky Way. This cluster is an intruder, a piece of another cosmic city that we are in the middle of swallowing. By studying its stars, Astronomers are not just learning about a cluster, they are reading the chemical history of an entirely different galaxy. Its stars have a distinct chemical signature, a different recipe of heavy elements that tells us about the unique conditions in its original, smaller home. This discovery fundamentally changes the identity of many clusters. They are not all born here. Some were captured, their parent galaxies shredded by our galaxy's immense gravity, leaving only their brightest and most tightly bound cores to continue orbiting as ghostly trophies. The process is like finding a distinct, foreign stone embedded in a local riverbed, proving that a great flood once washed through, carrying treasures from a faraway land. This means that when we look at the star clusters in our halo, we are looking at a galactic archaeological dig, a collection of ruins from conquered neighbors. Each one tells a story of a collision, a merger, and a meal on a truly cosmic scale. These stellar immigrants are not always found as intact clusters. Sometimes the only evidence of their existence is a faint cosmic scar stretched across the sky. Across the vast, dark halo of our galaxy, astronomers have mapped colossal rivers of stars, flowing in graceful, silent arcs. These are tidal streams, the final, dissolving threads of ancient star clusters that strayed too close to the Milky Way's immense gravitational pull. They are the ghosts of globular clusters, completely torn apart over billions of years. The process is a slow, inexorable unraveling. A cluster on a long, elliptical orbit around the galaxy will feel a stronger gravitational tug from the Milky Way's core when it is at its closest approach. This differential force, the same that causes ocean tides on Earth, stretches the cluster. Over countless orbits, the cluster is pulled apart like cosmic taffy, its stars strung out into two long, shimmering tails, one leading ahead of it and one trailing behind. Mapping these streams is a monumental task. It involves using powerful telescopes to survey the sky and measure the precise positions, distances, and motions of millions of individual stars. When scientists find a group of stars all moving together at the same velocity, on the same path, through the galactic halo, they know they have found a stream. It is like spotting a school of fish in a vast, dark ocean by tracking their synchronized swimming. The most famous of these is the GD1 stream, a pristine stellar river that is the remnant of a cluster destroyed long ago. By tracing its elegant curve, scientists can not only reconstruct the orbit of the original cluster, but also use the stream as a sensitive probe. Any kinks or gaps in the smooth flow of stars could be the telltale sign of a recent, close encounter with a dark matter subhalo, an invisible clump of the universe's most mysterious substance. These stellar rivers are more than just fossils. They are dynamic tools, allowing us to map the invisible gravitational landscape of our galaxy and witness the ongoing, destructive ballet between star clusters and the galaxy they call home. These stellar rivers are not the only evidence of clusters losing their members. Some stars are not gently stripped away, but violently catapulted into the void. Astronomers have clocked stars hurtling through the galaxy at millions of miles per hour, speeds so immense they are destined to fly right out of the Milky Way forever. These are hypervelocity stars, and many of them trace their origins back to the dense cores of star clusters. How does a cluster become a cosmic cannon, firing stars into intergalactic space? The primary suspect is a gravitational slingshot involving a massive object at the cluster's heart. In a cluster harboring an intermediate mass black hole, a binary star system can wander too close. The immense gravity of the black hole can violently disrupt the pair. One star gets captured into a tight orbit, while the other is flung away at a tremendous velocity, like a stone from a sling. This process converts the orbital energy of the binary into pure, linear speed for the ejected star. Another, even more powerful mechanism involves a supernova explosion in a tight binary system. When one star explodes, it can instantly lose over half its mass. The gravitational bond holding the binary together suddenly vanishes, effectively unlocking the companion star. Like a ball on a string when the string is cut, the surviving star is released, continuing its orbital velocity, but now with nothing to hold it back. It rockets away on a one-way trip out of the galaxy. Picture a roller coaster car disengaging from the chain lift at the peak, but instead of rolling down, it is launched straight up into the sky, never to return. These stellar cannonballs are more than just celestial curiosities. By tracking their paths backward across the sky, astronomers can sometimes pinpoint the very cluster they were ejected from, offering a unique way to probe the violent interactions happening within those crowded stellar metropolises. While hypervelocity stars are flung from clusters by immense forces, the clusters themselves seem to be held together by something less than we expect. These massive, ancient structures appear to be missing a key ingredient: dark matter. For decades, astronomers assumed that globular clusters, like galaxies, must be embedded within vast, invisible halos of this mysterious substance. Dark matter's gravitational glue is what prevents galaxies from flying apart. It seemed logical that the same would be true for these dense stellar cities. Yet, when scientists meticulously measured the motions of stars within globular clusters, they found a startlingly simple gravitational picture. The stars are moving precisely as fast as you would predict based on the combined gravity of all the visible stars alone. There is no extra pull, no sign of a hidden, massive halo of dark matter. This is a profound puzzle. How can a structure so massive and so old remain so stable without the cosmic scaffolding of dark matter? The answer may lie in their violent origins. One leading theory suggests that globular clusters formed not in the quiet dark matter halos of the early universe, but in the turbulent, gas-rich disks of the first galaxies. Intense bursts of star formation in these regions could have gathered vast numbers of stars into a tight, self-gravitating ball. This dense knot of stars, born from regular matter, would have such strong internal gravity that it could hold itself together for billions of years without any dark matter assistance. It would be a purely baryonic island in a dark matter-dominated cosmos. Another, more dramatic idea is that clusters did form with dark matter, but it was stripped away. If a cluster's orbit repeatedly carries it through the dense disk of its host galaxy, the galaxy's tidal forces could have slowly but surely ripped the loosely bound dark matter halo away, leaving only the tightly packed stars behind. This is like a comet passing too close to the sun, losing its icy tail, but on a cosmic timescale and with an invisible component. The debate is far from settled, and this absence forces a fundamental question. Are globular clusters fundamentally different from the smallest galaxies, which are known to be dominated by dark matter? This puzzling lack is more than an oddity. It is a crucial test for our models of how all cosmic structures, from the smallest clusters to the largest galaxies, are built. The absence of dark matter is not the only way star clusters defy our simple classifications. A deeper mystery lies in their very DNA. For generations, astronomers held a simple belief: a star cluster is born from a single, collapsing cloud of gas, creating a family of stars that all share the same age and the same chemical composition. They are cosmic twins, born from the same primordial stuff. But when we read the chemical fingerprints of stars within ancient globular clusters, the story becomes far more complex. We find not one family, but several. The stars reveal multiple, distinct generations. The first generation is exactly as predicted. These are the pristine, ancient stars, forged from the pure hydrogen and helium that filled the early universe. They are the cluster's founding population. Yet, mixed among them are second, and sometimes even third, generations of stars. Their light reveals a crucial difference. Their atmospheres are polluted with heavier elements like oxygen, nitrogen, and aluminum. This is a chemical signature they should not possess if they formed from the original, untainted gas. So where did this chemical enrichment come from? The answer points to a dramatic cycle of life and death within the cluster itself. The most massive stars in that first generation lived fast and died young, exploding as supernova or blowing off their outer layers in powerful winds. These violent deaths seeded the remaining gas within the cluster with newly forged heavy elements. This enriched gas, now polluted with the ashes of its dead predecessors, then collapsed to form a new wave of stars. These second-generation stars were born from the recycled remains of the first. Think of it like a forest growing on its own ashes. The first generation of trees grows from the pure soil. When they die and fall, they decompose, enriching the ground with new nutrients. The next generation of trees that sprouts is fundamentally different, growing taller and stronger from that enriched soil. This process shatters the old idea of a single, rapid burst of star formation. It reveals that some clusters were dynamic factories, capable of multiple rounds of stellar birth, separated by millions of years. The puzzle, however, is one of survival. The ferocious energy from the first supernova should have blown all the remaining gas clean out of the cluster, shutting down production forever. How did enough of this polluted gas remain behind to collapse and form new stars? This is one of the greatest unresolved questions in cluster science. It suggests that the early environments within these clusters were far more complex and turbulent than we ever imagined, with pockets of gas somehow shielding themselves from the violence or falling back into the core after the initial fury subsided. This discovery of multiple generations forces us to see these glittering swarms not as simple, frozen snapshots of the past, but as evolving ecosystems with their own intricate life cycles. The chemical complexity of stellar generations is matched by another, more visible mystery, the strange case of the yellow supergiants. Within certain young, massive star clusters, astronomers are finding far too many of these luminous yellow stars. These are not the ancient, stable stars of globular clusters, but titans in the final, dramatic chapters of their lives. A yellow supergiant is a massive star that has exhausted the hydrogen fuel in its core and is now undergoing a complex and brief transition. It swells enormously, cooling from its original blue-hot state to a yellow-orange hue, on its way to becoming an even larger red supergiant before it explodes as a supernova. According to our best models of stellar evolution, this yellow phase should be incredibly fleeting, a quick stopover lasting perhaps only a few tens of thousands of years. In the grand life of a star that lives for millions, this is a mere blink. Because it is so brief, we should only ever see a handful of these stars in any given cluster at one time. Yet, when we look at clusters like those in the Magellanic Clouds, our galactic neighbors, the numbers do not add up. There are not just a few. There is an overabundance, a crowd of yellow supergiants where our theories predict only a sparse population. This is more than simple counting error. It is a direct challenge to our understanding of how the most massive stars behave as they die. It suggests that something is wrong with our stellar models. Perhaps these stars spend much longer in this transitional phase than we thought, or maybe they evolve in a more complex, looping path that we have not fully charted. Imagine predicting that a rare flower blooms for only one day a year, but when you visit the field, you find it filled with blossoms for an entire season. Your understanding of its life cycle is clearly incomplete. This yellow supergiant problem forces astronomers back to the drawing board, compelling them to re-examine the intricate physics of stellar interiors, convection, and mass loss during these final, volatile stages. It is a stark reminder that even the life cycles of the most brilliant stars still hold profound secrets. While yellow supergiants appear in surprising numbers, other stellar elders are strangely absent. A different kind of puzzle emerges when astronomers count the red giant stars in certain clusters. A red giant is the final, glorious stage for a star like our own Sun. After billions of years of steady burning, it exhausts the hydrogen in its core and begins to swell, cooling into a vast, luminous orb. Our models of stellar evolution are quite precise. We can predict, for a cluster of a given age and composition, exactly how many stars should be in this red giant phase at any one time. Yet, in some clusters, the numbers fall short. A significant fraction of the red giants we expect to see are simply not there. It is as if a whole generation of retirees has vanished from a small town, leaving empty rocking chairs on the porch. This is the missing red giants problem, and its solution forces us to look at the final, unstable years of a star's life. The transition into a red giant is not a smooth one. For stars of a specific mass range, it is marked by a violent internal event known as a helium flash. This is not an explosion that tears the star apart, but a sudden, furious ignition of helium in the star's core. For decades, we assumed this flash was a standard, predictable process. But what if it isn't? What if, for some stars, this internal convulsion is far more violent than our models suggest? One compelling theory is that a particularly powerful helium flash could lead to catastrophic mass loss. Instead of the star gently puffing away its outer layers over time, a violent flash might blast a huge portion of the star's atmosphere into space in one dramatic event. This would strip the star down prematurely, skipping the long, stable red giant phase altogether and hurrying it toward its final fate as a white dwarf. Imagine an engine backfiring so violently that it blows its own hood off, shutting down the vehicle before it can even complete its journey. This would leave the star in a different, less luminous state that we might not easily recognize as a former red giant. Another possibility is that our understanding of mass loss is fundamentally incomplete. Perhaps the steady stellar winds that carry material away from an aging star are far stronger than we calculate, causing the star to shed its mass so efficiently that it never swells into the large, bright red giant we expect to observe. The absence of these stars is more than a head count. It is a direct challenge to our models of stellar death, suggesting that the final chapters of a star's life can be far more abrupt and tumultuous than the quiet, predictable fade we once imagined. The absence of expected stars is a haunting clue, but some clusters present an even richer archaeological puzzle. Nestled deep within the galactic bulge, the star cluster Terzan 5 stands as a cosmic fossil of unparalleled strangeness. Unlike the relatively uniform globular clusters we have encountered, Terzan 5 is a chaotic mix of stellar generations. Its stars tell two wildly different stories. One population is ancient, nearly 12 billion years old, with a very low iron content, typical of the universe's first stars. The other population is significantly younger, a mere 6 billion years old, and astonishingly, its iron content is 3 times higher. This is a staggering variation, a chemical gulf that should not exist within a single, coherent cluster. It is as if an ancient Roman ruin were found with a modern steel skyscraper built directly at its center, both structures standing together as one. This profound disparity shatters the standard model of cluster formation. A single collapsing gas cloud could never produce two families of stars so different in both age and composition. So what is Terzan 5? The most compelling theory is that we are not looking at a true globular cluster at all, but at the surviving nucleus of a primordial galaxy. In the early universe, the Milky Way's central bulge was built through the violent mergers of many smaller, gas-rich building blocks. Terzan 5 could be the fossilized core of one of these foundational fragments. In this scenario, the ancient iron-poor stars represent the original inhabitants of that dwarf galaxy. Then, about 6 billion years ago, this proto-galaxy experienced a second major burst of star formation. This new wave of stars was born from gas that had been enriched with iron by generations of supernova from the first population. This gas could have been native to the dwarf galaxy itself, or perhaps it was captured during a close encounter with another building block. This dual identity makes Terzan 5 a unique time capsule. It is a living record of the very construction process that formed the Milky Way's crowded heart. Its stars are witnesses to the chaotic mergers and intense star-forming events that built our galactic center. The cluster's incredible density allowed it to survive the violent process of assimilation, while lesser structures were torn apart completely. Terzan 5 is more than a cluster. It is a galactic ghost, a direct line back to the era of assembly, forever holding the two-tone story of its own birth and the birth of our galaxy. Deep within the swirling cores of globular clusters, another class of cosmic oddity defies expectation: the strangely silent millisecond pulsar. These stellar remnants are the universe's ultimate timekeepers, spinning hundreds of times per second and emitting brilliant, rhythmic pulses of radiation like cosmic lighthouses. Traditionally, we find them by listening for their powerful radio wave broadcasts. Yet in the crowded stellar cities, astronomers have found a population that breaks this rule. They are incredibly bright in high-energy X-rays or gamma rays, but whisper quiet in the radio frequencies we expect to hear. It is like finding a brilliant, flashing beacon that is completely silent, its light screaming into the void while making no sound at all. This radio silence is a profound puzzle. Our entire model of how pulsars work is built on the idea of powerful radio beams generated by intense magnetic fields and rapid rotation. So what could possibly turn off the radio while amplifying the high-energy light? The answer may lie in their crowded environment. One leading theory suggests these pulsars are drowning in a sea of stolen gas. In a dense cluster, a millisecond pulsar often has a binary companion. If the stars are close enough, the pulsar's gravity can pull a continuous stream of material from its partner. This incoming gas, falling at near light speeds, forms a swirling, superheated disk around the pulsar's magnetic poles. This raging torrent of plasma could be acting as a shroud, absorbing or scattering the radio waves before they can escape into space. Meanwhile, the incredible violence of this accretion process, the gas slamming onto the pulsar's surface, generates tremendous heat, glowing fiercely in X-rays. Another possibility is that the magnetic fields of these pulsars are simply configured in a way we do not yet understand, perhaps weaker or differently aligned, channeling their energy into particle acceleration and gamma rays instead of radio broadcasts. These quiet pulsars force us to reconsider the life cycle of these spinning corpses. They are not just isolated beacons, but deeply social stars, whose behavior is radically altered by the cosmic company they keep. Their silence speaks volumes about the complex and dynamic interactions that define a star cluster's heart. The silence of these strange pulsars is broken by the roar of stellar titans on the run. Far from the crowded cores where they were born, astronomers have discovered massive, luminous stars racing alone through the emptiness of interstellar space. These are the runaway stars, and their solitary journeys tell a violent story of their origins. A star does not simply pack its bags and leave its stellar family. To be flung out at speeds exceeding 100,000 miles per hour requires a cosmic catastrophe. The most likely culprit is a close gravitational encounter in the dense core of a young cluster. Imagine a binary star system, two massive stars orbiting one another, swinging too close to the cluster's central black hole or another, even more massive binary pair. The gravitational chaos can act like a slingshot, capturing one star and violently ejecting its partner, sending it careening into the void. Another dramatic method involves a supernova kick. If one star in a tight binary explodes, the sudden, asymmetric blast can literally kick the entire system. The surviving companion, now suddenly freed from the bond of its exploded partner, recoils and flies away at immense speed. We identify these runaways by their incredible velocity and their isolation. They are the brilliant blue O-type or B-type supergiants found impossibly far from any known star-forming region, their paths traced backward across the galaxy to the very clusters that expelled them. Their trajectories are cosmic evidence, frozen in motion, pointing directly back to the scene of the crime. Each runaway star is a smoking gun, its flight path revealing the hidden gravitational violence occurring within the stellar nurseries it once called home. The silent, runaway stars are not the only messengers from a violent past. Centuries after a star explodes, its ghost can still be seen. In the sprawling star cluster known as the Large Magellanic Cloud, astronomers witnessed something truly miraculous, a supernova replaying itself. The original cataclysm, witnessed by earthly observers in the year 1987, had long since faded from view. But then, years later, a faint, glowing ring of light began to appear around the remnant, slowly expanding outward like a ripple on a cosmic pond. This was no new explosion. It was a light echo, the initial, unimaginably bright flash from the supernova had raced outwards at light speed, but some of that light did not travel directly to our telescopes. Instead, it slammed into vast, previously invisible sheets and clumps of interstellar dust surrounding the cluster. This dust, heated by the flash, re-radiated the light, sending it on a delayed, longer journey to Earth. We are not seeing the actual event a second time, but its reflection, a cosmic recording played back from the vault of space. This echo provides a unique opportunity. By studying the spectrum of this reflected light as the ring expands, scientists can effectively re-observe the supernova's initial outburst from different angles, analyzing the physics of the explosion in a way that was impossible with the single, fleeting flash we saw decades ago. It is like finding an old recording of a historic event, but from a camera angle you never knew existed, revealing details that change your understanding of what actually happened. This delayed replay, born from the interaction between a star's death cry and the silent dust of its home cluster, gives us a second chance to interrogate one of the universe's most powerful events. The ghostly echoes of ancient supernova are not the only remnants of violence within these clusters. Some stellar cities appear to be hiding a monstrous secret at their core, one that breaks all the established rules. Astronomers studying a particular globular cluster found evidence of a gravitational anchor so immense it defies comprehension. This is an overmassive black hole, a behemoth whose sheer size does not fit the standard scaling relations we see everywhere else in the universe. In galaxies, there is a clear and predictable correlation between the mass of the central supermassive black hole and the mass of the galaxy's central bulge. The bigger the galaxy, the bigger its black hole. This relationship is so consistent, it feels like a fundamental law of cosmic construction. Yet, in this dense, ancient cluster, scientists found a black hole that is far, far too large for its stellar neighborhood. Its mass is hundreds, perhaps even thousands, of times greater than any model would predict for a cluster of its size and stellar population. It is like finding a skyscraper-sized engine inside a compact car. How could such a disproportionate monster form? The discovery sent shockwaves through the astronomical community, as it challenges our most basic ideas about how black holes and their host systems co-evolve. One radical theory suggests this is not a black hole that grew with the cluster, but a primordial black hole, a relic from the universe's first second, that simply trapped a swarm of stars around it. Another, more dynamic idea proposes that this black hole is a serial cannibal. At the center of the dense cluster, it could have devoured countless smaller black holes and neutron stars, merging them into a single, overgrown titan through a long and violent history of cosmic consumption. This finding forces a profound question. Are we looking at a rare anomaly, or is our understanding of the relationship between black holes and their homes fundamentally flawed? The rules we thought governed cosmic structure might be mere suggestions in the chaotic reality of these ancient stellar metropolises. The line between a star cluster and a galaxy is far more fragile than we ever believed. Consider the mysterious object known as FSR 1767. For years, it was catalogued as just another faint, distant globular cluster orbiting our galaxy. But its true nature was a cosmic masquerade. When astronomers pointed more powerful telescopes toward it, they discovered something profoundly unsettling. The stars within FSR 1767 were not packed into the tight, spherical ball typical of a globular cluster. Instead, They were scattered in a loose, elongated stream, a shape that spoke of immense disruptive forces. This was not a cohesive stellar family holding itself together. It was a ghost, the final, dissolving skeleton of a dwarf galaxy that had been torn apart by the Milky Way's gravity. The cluster was an illusion, a temporary gathering of stars that were merely the last survivors of a much larger system, now completely shredded. How could we have been so mistaken? The answer lies in our own perspective. From our vast distance, a sparse, stretched-out remnant can appear as a single, fuzzy point of light, easily confused with a true, dense cluster. It is like mistaking a scattered group of shipwreck survivors clinging to driftwood for a single, solid island. The discovery of FSR 1767's true identity forced a major re-evaluation of our cosmic catalogues. It revealed that our galaxy's halo is littered with these phantom clusters, the last glowing embers of galactic systems that no longer exist. This blurs a fundamental boundary in astronomy. What truly defines a galaxy? Is it simply a question of size, or is it the presence of dark matter, that invisible glue that globular clusters seem to lack? These phantom objects sit in a strange gray zone, challenging our very definitions and reminding us that the cosmos is full of shapeshifters, where what we see is often just the echo of a far more dramatic and violent history. Our cosmic classifications face an even deeper challenge from the very chemistry of the stars. Astronomers have catalogued clusters whose chemical fingerprints are utterly alien, bearing no resemblance to any known stellar population within our galaxy. These are not just subtle variations, but radical anomalies in the fundamental building blocks of matter. The specific ratios of elements like magnesium and potassium are wildly off-kilter, defying every established model of how stars cook elements in their nuclear furnaces. This is not a simple case of pollution from a previous generation. This is evidence of nucleosynthesis processes we have never witnessed, exotic pathways for forging atoms that do not seem to occur in the stars we understand. Imagine discovering a library of books written in a language that uses a completely unknown alphabet, its grammar and structure unlike anything you have ever seen. That is the level of mystery these chemical abundances present. One leading hypothesis points to the environments within the very first primordial star clusters. The first stars in the universe were behemoths, hundreds of times more massive than our Sun. Their internal furnaces burned at temperatures and pressures far beyond anything in modern stars, potentially triggering rare nuclear reactions that produced these strange elemental cocktails before they exploded. The clusters we see today, with their anomalous chemistry, could be the direct descendants of those first violent stellar factories. Their stars carry the unique isotopic signature of a bygone era, a recipe for elements that was lost when those first giant stars vanished from the cosmos. Another, even more exotic idea involves the insanely dense collisions of neutron stars. When these stellar corpses spiral together and merge, they are forges for the heaviest elements in the universe, like gold and platinum. But perhaps under certain extreme conditions, they also produce bizarre overabundances of lighter elements like potassium in ways we have not yet modeled. These chemical outliers are more than just cosmic oddities. They are direct probes into the most extreme physics the universe can produce, challenging our very understanding of how matter is created and reminding us that the periodic table still has chapters we have yet to read. These chemical riddles are mirrored by stars that refuse to follow the standard path of stellar life. In the orderly chart that astronomers use to classify stars, known as the Hertzsprung-Russell diagram, every star has its expected place. But within certain clusters, we find a population of rebels, stars that have strayed far from their designated positions, creating a strange and extended horizontal branch. This is not a mere plotting error. It is a sign of stars with deeply complicated personal histories. A horizontal branch star is a late stage in the life of a sun-like star. After its red giant phase, it settles into a stable period of burning helium in its core, becoming a compact, hot star. In a typical cluster of a given age, all these stars should cluster together in a tight, horizontal group on the diagram, all with similar temperatures and colors. But in some clusters, this branch is not a neat line. It is stretched out, with stars scattered into regions that are far too hot or far too cool to fit the standard model. Why are these stars so different from one another? The answer seems to lie in events that happened long before they reached this stage. The key factor is how much mass a star managed to hold onto during its chaotic red giant phase. Think of two identical cars starting a race. One driver is cautious, conserving fuel. The other driver has a leak in their gas tank, losing fuel rapidly along the way. By the end, the second car is running on fumes, fundamentally changed by the journey. This is the story of these extended, horizontal branch stars. Some of them have lost an extraordinary amount of their outer hydrogen envelope. A star that loses a huge amount of mass will shrink down to an extremely hot, helium-burning core, appearing on the far left, blue end of the horizontal branch. Another star in the same cluster, perhaps through a gentler mass loss process, retains a thicker envelope and remains cooler, settling on the red end. But what causes such wildly different amounts of mass loss in stars that were born as twins? The suspects are numerous. Stellar rotation could be a major player. A star that spins rapidly might be more effective at flinging its own material into space. Or perhaps the influence of a binary companion is at work, gravitationally stripping the star over billions of years. Some astronomers even speculate that planets falling into their aging host star could trigger extra mass loss. This extended branch is more than just a scattering of points on a graph. It is a forensic record, a celestial crime scene where the clues point to a turbulent past of stellar spin, cosmic companionship, and dramatic self-sacrifice. These stars are telling us that the quiet, predictable aging we once imagined is anything but, and that the final stages of a star's life are shaped by a lifetime of unique experiences. These graceful arcs of starlight are the final chapters in a cluster's life story, stretching across thousands of light years. Tidal tails are the visible proof that even the most tightly bound stellar families are not permanent. They are the result of a relentless gravitational tug-of-war. As a globular cluster orbits the galactic center, it does not feel a uniform pull. The side of the cluster closest to the Milky Way's core feels a stronger gravitational pull than the side farther away. This difference in force, the same that causes ocean tides on Earth, creates a stretching effect. Over billions of years, this constant tidal pull acts like a cosmic rack, slowly drawing stars out from the cluster's main body. The stars that are most vulnerable, those on the outer edges with the weakest gravitational bond to the cluster's core, are the first to be peeled away. They do not fly off randomly. Instead, they form two long, elegant streams, One stream leads ahead of the cluster in its orbit, while the other trails behind, creating a vast stellar river flowing through the galactic halo. Observing these structures requires immense patience and powerful telescopes. Astronomers must map the positions and motions of millions of individual stars to find those moving in synchrony. It is like identifying a single school of fish in a dark, vast ocean by their shared direction of travel. The discovery of these tails transforms our understanding of clusters from static islands into dynamic, evolving systems with a finite lifespan. We are not just looking at a cluster, we are witnessing its slow-motion dissolution, a real-time view of a cosmic death that takes billions of years to complete. This cosmic masquerade reaches its peak with objects that defy all simple labels. They are the ultra-compact dwarf galaxies, stellar systems so dense and massive, they were mistaken for mere star clusters for decades. At first glance, an ultra-compact dwarf looks like a particularly beefy globular cluster, a tight sphere of millions of stars, but its sheer mass gives it away. An ultra-compact dwarf can be hundreds of times more massive than the most enormous globular cluster, packing a staggering number of stars into a region only about 200 light-years across. This incredible density is the first clue that we are not looking at an ordinary family of stars. The debate over their true nature is a fierce one in astronomy. Are they simply the most massive star clusters ever formed, or are they the stripped-down corpses of small galaxies? The evidence increasingly points to a violent galactic origin. The leading theory suggests that ultra-compact dwarfs are the surviving nuclei of dwarf elliptical galaxies that ventured too close to a giant galaxy like our own. Imagine a small stellar city flying past a galactic metropolis. The immense tidal forces of the larger galaxy act like a cosmic thresher, violently stripping away the outer layers of the dwarf galaxy. All the loosely bound stars in its halo and disk are shredded into faint streams, leaving behind only the brightest, most tightly bound core. This naked core, now isolated and incredibly dense, continues its orbit as an ultra-compact dwarf. We are not seeing a born cluster, but a galactic ghost, the heart of a system that was otherwise completely devoured. Supporting this grim origin story are the dark secrets these objects seem to hold. Many ultra-compact dwarfs exhibit signs of having central black holes with masses far larger than any found in a true globular cluster. Some even appear to contain significant amounts of dark matter, that mysterious gravitational glue that globular clusters famously lack. This is the final, telling piece of the puzzle. A true star cluster is a structure built from stars alone, but a galaxy, no matter how small, is defined by the dark matter halo that birthed it. The presence of this invisible skeleton within ultra-compact dwarfs strongly suggests they are not clusters at all, but the smallest and most dense galaxies ever discovered. They represent a fundamental boundary in the cosmic hierarchy, a place where the definitions we created are blurred by the universe's messy, violent reality. A globular cluster should be a placid, slowly churning sphere of stars, its movements governed by billions of years of gravitational relaxation. Yet the core of the great cluster, 47 Tucani, tells a different story. Here, thousands of stars are caught in a distinct, swirling current, a rapid rotation that defies our expectations for such an ancient system. This is not a gentle drift. The inner core of this cluster spins with a surprising velocity, a coordinated motion that suggests it has somehow retained the angular momentum from its birth over 12 billion years ago. How can this be? Our models predicted that any initial spin should have been erased long ago through dynamical friction, a process where stars interact gravitationally and gradually randomize their orbits, sapping the overall rotation. The persistence of this fast-spinning heart is a direct challenge to that timeline. It implies that the cluster's core is far more resilient, its internal dynamics preserving a fossil record of its original spin, like a cosmic flywheel that never slowed down. The evidence comes from painstaking measurements of stellar motions, where astronomers can detect the subtle blue shift of stars moving toward us on one side of the core, and the redshift of stars moving away on the other. This clear signature of rotation is found in several massive clusters, painting a picture of dynamic cores within seemingly serene globular swarms. The implications force a rethink of their entire life story. Perhaps these clusters did not form from a single monolithic collapse, but through a more hierarchical process where smaller, spinning star groups merged together, their combined angular momentum fueling the rapid spin we see today. Or maybe the answer lies in the hidden influence of an intermediate mass black hole, its gravity orchestrating the stellar dance into a coherent whirl. This unexpectedly swift rotation is more than a curious detail. It is a fundamental clue written in the motion of 10,000 suns, pointing to a far more dramatic and structured origin for these ancient celestial cities. A star cluster's true population often hides in its faintest members, the countless red dwarf stars that should vastly outnumber their brilliant siblings. Yet when astronomers take a census of certain globular clusters, they come up short. A curious deficit of these low-mass, dim stars appears, as if a vast portion of the cluster's population has simply vanished. According to the universal initial mass function, a rule that predicts how many stars form at each mass, for every massive, luminous blue giant, there should be a veritable sea of these small, cool red dwarfs. But the numbers do not add up. The faint end of the stellar population is strangely quiet. So where have all the small stars gone? One compelling explanation points to a process of dynamical friction, a slow gravitational sinking. In the crowded core of a cluster, stars are constantly interacting. The more massive stars tend to sink toward the center over time, while the lighter stars can be given gravitational kicks that send them drifting outward. For the very lowest mass stars, these interactions can be so effective that they are gradually nudged all the way to the cluster's outer halo, or even ejected completely into the galactic void. Imagine a crowded dance floor where the largest, most forceful dancers gradually push their way to the center, while the lighter, less massive ones are steadily shuffled to the edges, some stumbling out the door entirely. This slow-motion segregation could explain why some clusters appear depleted of their faintest citizens when we look at their bright cores. An even more dramatic possibility is that these small stars were never there to begin with. The primordial conditions in the gas cloud that formed the cluster might have been fundamentally different. Perhaps the gas was so hot and turbulent that it fragmented into larger pieces on average, producing a top-heavy population with fewer low-mass stars from the very start. This would mean the initial mass function is not as universal as we thought, but can be shaped by the extreme environment of a nascent cluster. The silence of the missing red dwarfs is a profound clue. It forces us to ask whether these clusters are slowly evaporating their smallest members, or if they were born with a fundamentally different stellar recipe, one that challenges our understanding of star formation itself. Among the most violent and unpredictable stars in the cosmos are the luminous blue variables. These are not stable, aging giants, but colossal, unstable behemoths perched on the edge of catastrophe. They are the true divas of the stellar world, prone to gigantic outbursts that can outshine entire galaxies for brief, spectacular periods. Within the crowded confines of a star cluster, such a star becomes a celestial tyrant. Its violent mood swings dictating the environment for light years around. A single one of these stars can contain 50 times the mass of our Sun, burning with a ferocious intensity that makes their lifetimes short and turbulent. Their defining characteristic is their instability. They do not simply shine, they convulse. Every few decades, or even centuries, a luminous blue variable may shed an enormous portion of its own mass in a titanic eruption. It is not a gentle stellar wind, but a catastrophic belch of stellar material, ejecting shells of gas equivalent to the mass of entire planets out into space at incredible speeds. Imagine a volcano not spewing ash and rock, but violently expelling entire mountainsides of its own flesh into the sky. The aftermath of such an eruption is a glowing nebula, a shell of ejected gas illuminated by the furious star at its center, a monument to its own self-destruction. The impact on its home cluster is profound. For the neighboring stars, life next to a luminous blue variable is a constant state of siege. The intense ultraviolet radiation and powerful stellar winds from this monster constantly batter any nearby stellar nurseries, potentially shutting down the formation of new planets or even new stars. When it finally does erupt, the blast of radiation and the physical shockwave of ejected material can compress nearby gas clouds, triggering new star formation in a paradoxical act of creation through destruction, or it can utterly disrupt and disperse the delicate cradles of infant planetary systems. The most famous example is Eta Carinae, a stellar system within our own galaxy that underwent a colossal explosion in the 1840s, briefly becoming the second brightest star in the night sky. While not in a dense cluster, it shows us the scale of the violence we are dealing with. In a cluster, such an event would be a transformative disaster, reshaping the local ecology for millions of years. These stars are the ultimate proof that a single, brilliant member of a stellar family can hold the power of life and death over all its siblings, a luminous blue heart of chaos beating at the center of a glittering community. The serene beauty of a planetary nebula often masks a chaotic death. These glowing shells of gas, expelled by dying sun-like stars, are typically seen as smooth, elegant bubbles in the emptiness of space. But within the crowded confines of a star cluster, these final breaths take on a bizarre and tangled form. Astronomers have spotted intricate, knot-like structures woven throughout the nebulae in clusters, complex webs of denser gas that defy the simple, spherical models of stellar death. These are not gentle farewells. They are violent, structured expulsions, and their knots hold the key to understanding the turbulent environment of a star's final moments. The prevailing theory suggests that these knots are a direct result of the star's interaction with its own past. As the dying star pulses and sheds its outer layers in successive waves, a faster, later wind from the exposed hot core slams into the slower, earlier ejected material. This collision is far from uniform. Instabilities cause the slower gas to fragment and clump. Much like cream poured into hot coffee, will roil and form temporary islands before mixing. These clumps are then sculpted by the relentless stellar wind and radiation pressure, getting stretched and compressed into the intricate knots we observe. But within a star cluster, this process is amplified. The thin soup of gas that drifts between the stars, known as the intra-cluster medium, acts as a resisting force. The expanding nebula must plow through this material, creating an additional shock front that further confines and distorts the gaseous shell, enhancing the formation of these dense, tangled structures. It is a stellar death shaped by its neighborhood, its final form a fossil record of the pressure and resistance it faced. By studying the intricate patterns of these knots, scientists can read the history of the star's mass loss, measuring the speed and timing of its final gusts. Each knotted nebula is a cosmic autopsy, revealing that even in death, a star's story is written not in isolation, but in constant, dynamic conversation with the crowded city it called home. Deep within the gravitational heart of a globular cluster, a silent duel of unimaginable power may be unfolding. Theoretical models predict that these dense stellar cities are the perfect breeding grounds for binary black hole systems, pairs of these dark monsters locked in a tight orbital dance. The process begins with the cluster's immense density. Stars and the black holes they leave behind are packed so closely that gravitational encounters are common. Two solitary black holes can be drawn together, becoming a bound pair through a process called dynamical friction. Once formed, this binary black hole is a gravitational tyrant. It roams the cluster core, and when a third star or black hole ventures too close, a violent gravitational game of cosmic pinball ensues. The binary can eject the intruder at high speed, a process that transfers energy and causes the black hole's own orbit to shrink, bringing them closer together. This is how a cluster can forge the tightest, most extreme black hole pairs in the universe. While we have not yet directly imaged such a pair in a globular cluster, the evidence for their existence is compellingly indirect. Astronomers observe stars being flung from cluster cores at inexplicably high velocities, their trajectories pointing to recent encounters with an unseen, massive object. In some clusters, the very center appears to be strangely evacuated, as if a massive, unseen binary has cleared out the neighborhood through countless gravitational slingshots. The ultimate confirmation of these dark duos will come not from light, but from ripples in spacetime itself. As these black holes spiral ever closer, they are predicted to be prolific sources of gravitational waves. Future observatories will listen for the faint chirp of their final, merging embrace, a signal born from the chaotic, crowded core of a star cluster. These binary systems are not just theoretical curiosities. They are ticking clocks, counting down to some of the most energetic events in the cosmos, all hidden within the glittering piece of a star cluster's core. These youthful giants defy the very aging of their galactic homes. In the halos of massive, elliptical galaxies, composed almost entirely of ancient, red stars, astronomers have found glittering swarms that look impossibly young. These are massive globular clusters, but they burn with a blue, vigorous light that suggests they are mere infants, only a few 100 million years old. Their existence creates a stark cosmic contradiction. How can a galaxy that finished forming stars over 10 billion years ago suddenly produce such brilliant, new stellar families? The answer rewrites our understanding of galactic life cycles. It appears that these old galaxies are not entirely dead. They can experience a late life burst of creation, often triggered by a dramatic event. The most common catalyst is a galactic merger. When two gas-rich galaxies collide, their vast reservoirs of cold gas are violently stirred and compressed. This chaos creates the perfect conditions for the birth of not just individual stars, but of entire, massive clusters at once. It is a cosmic renaissance, a second spring for a galaxy that had long settled into a quiet retirement. Another possibility is the accretion of a much smaller, gas-rich dwarf galaxy. As this tiny system is torn apart by the larger galaxy's gravity, its gas is stripped away and funneled toward the center, igniting a final, concentrated burst of star formation that forges these new clusters. These young globulars are not just a curiosity. They are forensic evidence of a recent, violent meal, a permanent record of a galactic collision that occurred long after the main construction phase of the universe was over. They prove that even the oldest, most serene-looking galaxies can hide a surprisingly eventful recent past with the capacity for sudden, brilliant rebirth. The serene void between the stars is not always empty. Even in the ancient realms of globular clusters, where stellar winds and supernova should have scoured the environment clean billions of years ago, astronomers have stumbled upon a ghostly presence. They have detected faint, wispy clouds of cold hydrogen gas and microscopic dust grains drifting in the spaces between the suns. This is the intra-cluster medium, a tenuous atmosphere that, by all rights, should not exist. The presence of this material is a baffling anomaly. In the standard life story of a cluster, the first generation of massive stars would have lived and died in a fury. Their powerful winds and final, explosive deaths would have acted like a cosmic fire hose, blasting every last trace of unformed gas and dust out of the cluster's gravitational grip. Without this raw material, the star-forming factory shuts down forever. Yet here it is, a faint but undeniable mist. So where did this gas and dust come from? How was it replenished? One compelling theory points to the slow, steady contribution from the cluster's own aging population. As sun-like stars reach the end of their lives, they gently puff away their outer layers, creating beautiful planetary nebulae. While much of this expelled gas is hot and energized, some of it may eventually cool down and contribute to a faint, lingering reservoir. It is a form of stellar recycling, where the final breaths of dying stars provide the material for a potential future generation. Another, more dramatic possibility involves an external source. Perhaps the cluster, on its long orbit around the galaxy, recently plowed through a diffuse interstellar cloud. This chance encounter could have allowed the cluster to gravitationally capture a fresh supply of cold gas, a cosmic refueling that defies its advanced age. The discovery of this faint medium forces a profound shift in our perspective. These clusters are not entirely sterile, cleaned-out fossils. They may still possess a fragile, lingering ecosystem, a whisper of the raw materials that once built them, held in a delicate balance against the relentless radiation of their stellar inhabitants. This ghostly gas is a clue that the story of a star cluster may not have a final, closed chapter after all. Gamma-ray bursts are some of the most powerful explosions in the universe, and for years, a specific class of them defied explanation. These short-duration bursts, lasting less than 2 seconds, flashed across the cosmos without any trace of a host galaxy. They appeared to be orphans, seemingly born in the empty voids between galaxies, which made no sense. Such immense energy had to come from a cataclysmic source, but what catastrophic event could possibly occur in the nothingness of intergalactic space? The answer may lie in the very star clusters we have been exploring. The leading theory for these short bursts is the spectacular collision of two neutron stars. When these incredibly dense stellar corpses spiral into each other, they can create a black hole and unleash a furious blast of gamma rays in two narrow, opposing jets. If one of those jets is pointed directly at Earth, we see it as a brilliant flash. But why would these mergers happen far from any galaxy? The missing link is the incredible gravitational dynamics within globular clusters. A globular cluster acts as a perfect stellar matchmaker for neutron stars. Its dense core allows these dead stars to find each other, often forming tight binary pairs through gravitational interactions. Over billions of years, their orbits decay until they finally merge in a cataclysmic embrace. The resulting gamma-ray burst is so incredibly energetic that the kick from the merger can be powerful enough to eject the entire system, the newborn black hole and any surrounding stars, right out of the cluster and even out of its host galaxy. The burst itself is the final act, the brilliant flash of a merger that occurred while the system was being flung into intergalactic space. We see the flash from the orphaned event, but by the time the light reaches us, the source is already drifting in the cosmic dark, far from the glittering city that birthed it. This solves the mystery of the orphan bursts. They are not born in the void. They are exiles, their brilliant deaths marking a violent farewell to the crowded stellar homes they once knew. The glittering halo of a galaxy should be a sphere of chaos, a random swarm of ancient clusters collected from all directions over billions of years. But when astronomers map the positions of globular clusters around certain galaxies, they find something deeply unsettling. The clusters are not scattered randomly like marbles tossed into a sphere. Instead, they are arranged with a strange sense of order, aligned along vast, thin planes or flattened structures that cut through the galactic halo. This anisotropic distribution is a cosmic fingerprint, pointing to a single, violent event in the galaxy's past rather than a long, slow accumulation of random captures. It suggests that many of these clusters arrived together in one coherent group. The most striking example of this is found around our own Milky Way. A significant portion of its globular clusters, along with a handful of dwarf galaxies, are aligned within what is known as the vast polar structure. This is a colossal, disk-like plane that rotates around our galaxy, perpendicular to the main disk of the Milky Way. It is as if a giant left a thumbprint on the halo, a distinct plane of stellar systems, all moving in concert. How could such a structure form? The leading theory is both simple and dramatic. This alignment is the ghost of a massive, singular feast. Billions of years ago, the Milky Way likely devoured one very large dwarf galaxy in a single catastrophic merger. As that victim galaxy was torn apart, its own system of globular clusters, which would have orbited in a flattened disk, was stripped away and captured. But they were not scattered to the winds. Instead, they retained the memory of their original, ordered motion, settling into this vast, rotating plane we see today. This is not the chaotic jumble of many small snacks. It is the fossilized remains of one giant meal, a coherent stream of stellar trophies, all pointing back to a single defining moment of galactic cannibalism. This discovery forces a profound shift in our view of galaxy growth. The halos of galaxies are not built entirely from random, piecemeal acquisitions. They can be shaped by colossal, single events that leave behind a structured, rotating skeleton of clusters, a permanent monument to the most violent dinner date in cosmic history. Even the final, fading embers of stellar life can hide a deep thermodynamic secret. White dwarfs, the Earth-sized cores of dead stars, are supposed to be the universe's most predictable clocks. They have no internal energy source, shining only with the leftover heat from their former lives, and they should cool at a steady, calculable rate as they fade into blackness. Yet in the ancient globular cluster Messier 4, astronomers found white dwarfs that are stubbornly, inexplicably warm. They are cooling at a pace far slower than our best physics predicts, as if they possess some hidden furnace delaying their cosmic retirement. These are the supersaturated white dwarfs, and their prolonged glow points to a dramatic internal transformation. The leading theory is one of profound beauty. As a white dwarf cools over billions of years, the intense pressure in its core forces its carbon and oxygen atoms to snap into a rigid, crystalline structure. It is a slow-motion freezing, a transformation from a dense plasma into a solid cosmic diamond the size of a planet. This process of crystallization does not just happen. It releases a tremendous amount of latent heat, the same way water releases heat when it freezes into ice. For a white dwarf, this sudden release of internal energy is like throwing a massive log onto a dying fire, providing a fresh source of warmth that dramatically slows its overall cooling. This latent heat could be the secret fuel keeping these white dwarfs supersaturated with warmth for billions of years longer than expected. But crystallization might not be the only strange physics at play. Some scientists speculate that as the core solidifies, the still liquid outer layers undergo a separation, with heavier elements sinking and lighter ones rising in a process called sedimentation. This gravitational sorting also releases energy, providing yet another delay to the final fade to black. Picture a hot cup of coffee, but instead of just cooling down, it suddenly crystallizes and separates its cream, each process giving off a fresh pulse of heat that keeps it warm far longer than you could ever anticipate. These slow cooling white dwarfs are more than just stellar anomalies. They are celestial laboratories, their prolonged glow allowing us to test the physics of matter under conditions of extreme density that we could never hope to recreate on Earth. Their defiance of the cooling timeline forces us to look deeper into the quantum mechanics of crystallization and the final, secret lives of stars. New kind of cosmic flash adds another layer to the mystery. Across the universe, telescopes have picked up fleeting blasts of radio energy so powerful they outshine entire galaxies for a few milliseconds. These are fast radio bursts, and their origin has been one of astronomy's greatest puzzles. For years, they seemed to come from random points in the void, with no obvious source. But a breakthrough came when one of these incredibly energetic bursts was traced back to its home, not in deep intergalactic space, but within our own galaxy. And its source was a specific type of stellar corpse, a magnetar. A magnetar is a neutron star with a magnetic field so immensely powerful it could strip the information from every credit card on Earth from halfway across the solar system. This is where star clusters enter the story. These dense stellar cities are perfect factories for creating such extreme objects. The same violent dynamics that forge binary black holes and hypervelocity stars can also produce magnetas. In a cluster's core, neutron stars can collide, or a massive star could collapse in just the right way to create this intensely magnetized monster. The conditions are perfect for these cosmic powerhouses to form. So how does a magneta create a fast radio burst? The leading theory is a starquake. The magneta's crust is under unimaginable strain from the titanic magnetic fields twisted inside it. Occasionally, this crust cracks in a release of energy equivalent to thousands of nuclear bombs detonating at once. This quake sends a shudder through the star's magnetic field, accelerating particles to near light speed and generating an intense, coherent blast of radio waves that shoots out into the cosmos. Think of it like snapping a rubber band that's been wound to its absolute limit. The sudden release sends a violent shock through the air. For a magneta, that snap is a cataclysm, and the shock is a flash of radio light visible across the universe. This connection to star clusters is speculative but profoundly compelling. It suggests that at least some of these mysterious bursts are not coming from the empty dark, but from the most crowded and violent stellar neighborhoods imaginable. The same environments that create stellar cannibals and rogue planets might also be the engines behind these brilliant millisecond flashes, turning ancient star clusters into cosmic lighthouses, occasionally signaling their violent inner lives with pulses of raw energy. These stellar convulsions can leave behind ghostly evidence, vast and faint structures that linger for eons. Encircling certain stars within ancient clusters, astronomers have detected immense spherical shells of gas and dust. These are not the smooth, symmetrical bubbles of a typical planetary nebula. They are colossal, often distorted envelopes, some so vast they could engulf our entire solar system many times over. Their faint glow is a whisper from a cataclysmic event, the ghost of a star's violent past. The origin of these shells points to two dramatic possibilities, both born from the extreme social life within a cluster. The first is a titanic stellar eruption. A luminous blue variable or a similar hypergiant star does not die quietly. In one of its periodic convulsions, it can eject a shell of material equivalent to the mass of Jupiter or more, hurling it outward at tremendous speeds. This ejected shell continues to expand, cooling and fading over thousands of years, but never quite disappearing. It forms a fragile, glowing onion skin layer around the star, a permanent record of that one violent day in its long life. The second, more patient mechanism involves a close binary dance. In a tight stellar pair, one star can act as a vampire, slowly and steadily siphoning material from its companion. This stolen gas doesn't always fall directly onto the vampire star. Instead, it can form a vast, rotating disk or an outflow that eventually settles into a surrounding envelope. The process is so gradual that the shell builds up over millennia, a slow-motion exhalation from a star being consumed by its partner. Discovering these structures is a monumental challenge. Their light is incredibly faint, often drowned out by the brilliant glare of the central star and the collective glow of the cluster itself. Astronomers must use sophisticated filters and image processing techniques to isolate the delicate light of the shell, like trying to hear a single soft voice in a roaring stadium. One of the most famous examples is the shell around the star Mira in our own galaxy. Though it lives alone, finding such structures in a dense cluster confirms that these violent mass loss events are a fundamental part of the cluster ecosystem. Each shell is a fossil, By studying its expansion rate and chemistry, we can work backwards to determine the precise date and ferocity of the eruption that created it. These faint halos are more than just cosmic debris. They are the lingering atmospheres of stellar explosions, the silent witnesses to the private, violent dramas that unfold within the crowded stellar cities. Deep within these stellar metropolises, some dead stars shine with an impossible ferocity. We find X-ray binary systems burning hundreds of times brighter than any similar pair drifting alone in the galactic field. These are the overluminous X-ray binaries, and their staggering power is a direct product of their crowded birthplace. An X-ray binary is a partnership between a stellar corpse, a neutron star or black hole, and a living star. The dense remnant's immense gravity pulls gas from its companion. As this stolen material spirals down at nearly the speed of light, it heats up to millions of degrees, releasing a furious torrent of X-rays. In the quiet galactic disk, such systems are born from isolated binary stars that manage to survive the death of one partner. Their luminosity is limited by the natural, gradual transfer of mass. But inside a globular cluster, the rules of engagement are rewritten by violence. Here, these systems are not born from quiet companionship, but forged through dynamical encounters, close gravitational interactions between stars that would never meet in the lonelier galactic expanse. A solitary neutron star can be gravitationally captured by a passing star, or a pre-existing binary can be violently altered when a third star swings too close, rearranging the partnership and shoving the stellar corpse into a much tighter orbit around its new donor. This forced intimacy is the key to the overwhelming brightness. In a typical field binary, the stars maintain a respectful distance, but in a cluster-forged system, the neutron star or black hole is often placed into an incredibly tight orbit, sometimes circling its partner in just a few hours. At this proximity, the gravitational pull is ferocious, stripping gas from the companion star at a phenomenal rate. It is the difference between a gentle stream and a fire hose. This torrent of infalling gas slams onto the surface of the neutron star or into the accretion disk around the black hole, generating X-ray emissions so intense they can outshine 100,000 suns. These overluminous systems are not just brighter versions of the same thing. They are a different breed entirely. Their very existence and extreme nature, a direct signature of the chaotic social dynamics that define life inside a star cluster. They are the ultimate proof that in the cosmos, where you are born dictates not only your life, but the very ferocity of your death. Yet another chemical mystery lurks within the ancient stars of these clusters. In populations that are otherwise incredibly poor in heavy elements, astronomers find specific stars that are bizarrely rich in carbon. This is a profound contradiction. These clusters formed when the universe was young, from gas that had not yet been polluted by many generations of supernova. Their stars should be pure, composed almost entirely of hydrogen and helium, with only the faintest traces of anything else. Finding a star shining with the soot of carbon is like finding a pristine, ancient cave painting that inexplicably uses modern acrylic paint. The presence of these carbon-rich stars completely upends our understanding of how the first heavy elements were created and distributed. The puzzle is not just that carbon exists, but that it appears in such dramatic overabundance in a few select stars, while their neighbors remain chemically pristine. So where did this carbon come from? It cannot be from the cluster's initial gas cloud or all the stars would share it. The carbon must have been added later, like a single tree in a forest being artificially fertilized. The leading suspect is a binary companion that has since vanished. The theory goes like this. Billions of years ago, these carbon-rich stars were part of a tight binary system. Their partners were slightly more massive stars that lived faster lives. As those companion stars aged, they swelled into red giants and began to fuse helium into carbon in their cores. Through a process called dredge-up, this freshly forged carbon was carried by convection currents to the star's surface. Then, in a final act of cosmic generosity, the dying star transferred its carbon-rich outer layers onto the surface of the smaller star we see today. The donor star then completed its death, collapsing into a faint white dwarf that is now too dim to detect. The recipient star, now blanketed in stolen carbon, appears as a single ancient metal-poor star that is strangely rich in this one key element. This makes these stars not primitive at all, but the products of a long-dead partner, their atmospheres forever marked by a gift from a stellar ghost. This discovery forces us to see these ancient clusters not as simple collections of individual stars, but as dynamic systems where binary interactions have fundamentally altered the chemical identity of many members, hiding a complex social history behind their serene, glittering facade. The serene orbits of our own solar system are a cosmic fantasy within a star cluster's core. Here, entire planets can be stolen. The theory of tidal capture suggests that rogue worlds, planets untethered to any star, could be gravitationally snared during a close stellar flyby. These are not planets born in the calm disk of gas around a newborn sun. They are cosmic orphans, adopted into a new family through a fleeting moment of gravitational chaos. Imagine two stars passing within a few billion miles of each other, a near miss on the galactic scale. Drifting between them is a dark, frozen world, ejected from its own system long ago. As the stars swing past, their combined gravity acts like a net, catching the rogue planet and pulling it into a new, often wildly elliptical, orbit around one of the stars. This process would not create the neat, circular paths we are familiar with. The captured world would be flung into a stretched, eccentric orbit, a trajectory that speaks of a violent and recent past. What would such a system look like from the surface of that captured world? Its year would be a roller coaster, swinging from a brief, scorching close approach to its new sun, out to a long, frigid journey into the deep freeze of the outer system. The possibility of tidal capture solves several puzzles at once. It offers an origin story for the giant exoplanets we have found on incredibly tilted or backward orbits, paths that are nearly impossible to achieve through standard formation models. It also provides a potential home for the billions of free-floating planets that are predicted to roam the galaxy, giving these dark wanderers a second chance at circling a star. This means the planetary census of a star cluster is not fixed. It is a dynamic ledger, with worlds constantly being ejected from some systems and captured by others, a continuous gravitational exchange that forever rewrites the map of these crowded stellar cities. These ancient stars, born as cosmic twins, should share an identical chemical signature, yet when astronomers analyze their light, they find a bewildering spread in the simplest of ingredients. Stars within the very same cluster show wild variations in their abundances of sodium, oxygen, and aluminum. This is not a subtle difference. Some stars are sodium-rich, while their immediate neighbors are sodium-poor. In others, oxygen is dramatically depleted, as if something had systematically stripped it away. These are light elements, the building blocks forged in the universe's first minutes and inside the first generations of stars. Their uneven distribution is a direct challenge to the idea of a single, simple birth for a globular cluster. This pattern is the smoking gun for the theory of multiple populations. It tells us that the gas which formed these stars was not pristine. It had been profoundly altered. The most massive stars in the first generation are the prime suspects. As they lived their short, violent lives, they fused hydrogen into helium deep in their cores. But in their final stages, powerful currents of convection, like a colossal stellar elevator, dredged up this processed material. This brought byproducts like aluminum and sodium to the surface, where intense radiation and stellar winds then blasted them out into the surrounding cluster environment. At the same time, the extreme temperatures in the cores of these massive stars also fused oxygen into other elements, effectively burning it up and creating pockets of oxygen-poor gas. Imagine a giant bakery where the first batch of bread is made from pure flour, but then the head baker starts mixing in various spices and seeds from the pantry into the leftover dough, creating a second, entirely different batch of loaves from the same initial stock. The stars we see today are those different loaves. The sodium-rich, oxygen-poor stars are the second generation, formed from gas polluted with the nuclear waste of their massive siblings. This self-enrichment process transforms the cluster from a single event factory into a complex ecosystem. The intricate variations we see, the specific levels of sodium depletion or aluminum enhancement in different stars, are like forensic clues. They allow scientists to piece together the exact mass and type of the stars that did the polluting, and the conditions under which that polluted gas later cooled and collapsed to form new stellar lives. This light element puzzle is not a minor detail. It is the chemical evidence of a dramatic and ongoing cycle of life and death, written in the atmospheres of the oldest stars in the universe. But the chemical ghosts of supernova are not matched by the physical ones. We have every reason to believe that thousands of these stellar cataclysms should have torn through globular clusters over their 12 billion-year histories. Each explosion would have left behind a glowing, expanding cloud of debris, a supernova remnant that should persist for tens of thousands of years. Yet when we train our most powerful telescopes on these ancient stellar cities, we find a profound and puzzling silence. The expected nebulous wreaths are simply not there. It is as if an ancient, bloody battlefield has been discovered, littered with the bones of the fallen, but without a single spent shell casing or a single crater to show for the violence. Where are all the supernova remnants? This absence is a deep cosmic contradiction. The very existence of multiple stellar generations, with their polluted chemical signatures, is direct proof that supernova did occur, seeding the cluster with heavy elements. So if the explosions happened, why can't we see their expanding remains? One compelling theory points to the unique environment of a globular cluster itself. These systems are incredibly dense, with stars whipping past each other at high velocities. When a supernova erupts, the resulting blast wave expands into this crowded neighborhood. Instead of ballooning freely into empty space, it immediately slams into the thin soup of gas and the powerful stellar winds flowing from thousands of neighboring stars. This relentless resistance acts like a brake, causing the remnant to dissipate its energy far more rapidly than it would in the lonely galactic field. The remnant's material is shredded, mixed, and heated, causing it to fade from view in just a few thousand years instead of the more typical 100,000. Its brief, brilliant flash is quickly swallowed by the churning, luminous background of the cluster itself. Another, more exotic possibility involves the very nature of the explosions. Perhaps the supernova that occurred in these primordial clusters were fundamentally different from the ones we see today. The first stars were behemoths, and when they died, they may have collapsed directly into black holes with a whimper instead of a bang, producing a feeble supernova or none at all. Or in the dense cluster core, a supernova's blast wave might be instantly overwhelmed and recycled, its material so quickly swept up into new star formation that a distinct remnant never gets a chance to form. This missing evidence forces us to reconsider the final moments of the first stars. Their deaths were not isolated events in a quiet vacuum, but violent convulsions within a roaring, stellar metropolis, their final cries muffled by the very crowd they helped create. Deep within the serene glow of ancient clusters, a different kind of star pulses with a rhythm that defies all expectation. These are the ultra-long period variables, stellar giants whose heartbeats are measured not in days or weeks, but in years. Their light rises and falls over cycles that can last hundreds, even thousands of days, a slow cosmic breathing that our current models of stellar interiors cannot fully explain. These are not the frantic pulsars or the predictable Cepheid variables. They are old, cool stars, often red supergiants, engaged in a mysterious, drawn-out dance. The sheer length of their cycle is the central puzzle. For a star to change its brightness so dramatically, its entire structure must be expanding and contracting, swelling to immense size before shrinking back down. But the physics that drives such a slow, grand oscillation remains elusive. It is as if we discovered a colossal bell that only tolls once every decade, and we cannot find the clapper that makes it ring. One leading theory suggests this could be a late, unstable phase of stellar life, where the star's outer layers become so extended and tenuous that they lose their grip on gravity. The star may be undergoing deep, convective turmoil, with massive bubbles of plasma slowly rising and falling over centuries, each one altering the star's diameter and brightness in a cycle we are only just beginning to clock. Another possibility involves a slow, rhythmic burning of nuclear fuel in a shell around the star's core, a feedback loop that takes an eternity to complete. Imagine a hot air balloon where the burner ignites only once every few years, causing the envelope to slowly inflate to a tremendous size before it gradually cools and deflates, starting the patient cycle all over again. These stellar elders are cosmic metronomes set to a tempo we can barely perceive, their long, slow breaths holding secrets to the final, unstable chapters in the lives of the largest stars. A star cluster's social hierarchy is brutally enforced by gravity itself. Within these glittering cities, a subtle but relentless sorting process is always at work, a phenomenon known as dynamical friction. It is a cosmic rule that larger, more massive objects will inevitably sink toward the center of a gravitational system, while lighter ones are pushed to the edges. Imagine a crowded dance floor where the biggest, most forceful dancers gradually work their way inward, while the smaller, lighter dancers are gently shuffled toward the walls. This is not a rapid event, but a slow, gravitational inevitability that plays out over millions of years. Every time a massive star swings past a lighter neighbor, its strong gravity gives the smaller star a slight gravitational kick, boosting its velocity. In exchange, the massive star loses a tiny bit of its own orbital energy, causing its path to decay just a little, drifting closer to the core. Over countless encounters, this process acts like a brake, systematically draining energy from the heaviest stars and black holes, guiding them downward into the cluster's dense heart. The result is a beautifully organized structure called mass segregation. The cluster's core becomes dominated by a glittering metropolis of massive stars, stellar remnants, and binary systems, while its outer halo is populated by a sparse sea of lower mass, dimmer stars. This gravitational sorting has profound consequences for the cluster's destiny. The dense core becomes a hotbed for dramatic interactions, forging the binary black holes, millisecond pulsars, and hypervelocity stars we have already met. But this very process also speeds up the cluster's eventual demise. As the most massive objects congregate in the center, their intense gravitational interactions act like a furnace, heating the core and making it expand. This pushes even more stars to the vulnerable outer edges, where the galaxy's tidal forces can easily strip them away, dissolving the cluster into a stellar stream. The very mechanism that creates a vibrant, dynamic core is also the one that ultimately seeds the cluster's destruction, a beautiful and tragic paradox written in the slow dance of stars. A star cluster's official boundary is a line drawn by gravity itself, the tidal radius. Beyond this invisible wall, the galaxy's pull should be too strong for any star to remain loyal to the cluster. Yet, when astronomers map the skies around these ancient families, they find renegades. These are the extra-tidal stars, solitary suns shining defiantly far outside their home's gravitational jurisdiction. They exist in a forbidden zone, a region where no star should logically remain bound. Their very presence is a clue to two radically different futures. One possibility is that we are witnessing the very first stage of a cluster's long, slow death. These stars are the early evacuees, gravitationally nudged just beyond the border by a close encounter with a neighbor or the cumulative effect of countless tiny tugs. They are the leading edge of the tidal tales we have discussed, the first few drips from a faucet that will eventually become a river, signaling the beginning of the end for the stellar city. But there is another, more mysterious explanation. What if these stars are not escaping at all? What if they are still bound, held in place by an unseen hand? This is where dark matter re-enters the story. We have learned that globular clusters seem to lack dark matter. But what if we are wrong? The presence of a vast, extended halo of dark matter, completely invisible to our telescopes, could provide the extra gravitational glue needed to hold these distant stars in orbit. In this scenario, the cluster we see is just the bright, visible core of a much larger, darker structure. These extra-tidal stars would then be tracers, the outermost sentinels of a massive, hidden fortress of dark matter, revealing that some clusters might be more like minuscule, dark matter-dominated galaxies than we ever believed. So are these distant stars the first to flee, or the last to be seen of a much larger entity? Their silent presence in the cosmic dark forces us to question the true size and nature of the star clusters we thought we knew. Lithium tells a story the stars are trying to erase. This simple element, one of the very first three created in the Big Bang, should be present in all the oldest stars at a predictable baseline level. Yet when astronomers measure the light from sun-like stars in globular clusters, they find a baffling inconsistency. The lithium in their atmospheres is dramatically depleted, often reduced to a mere fraction of the expected amount. It is as if someone has been systematically stealing pages from the universe's oldest history book. This is the lithium problem, and it strikes at the heart of two foundational pillars of modern cosmology: Big Bang nucleosynthesis and our standard models of stellar interiors. The Big Bang should have left a specific, universal fingerprint of lithium across the cosmos, a primordial abundance woven into the fabric of every first-generation star. The fact that these ancient cluster stars show so little of it means something has gone terribly wrong, either with our understanding of the universe's first moments or with our knowledge of how stars work. So where did the lithium go? If the stars are destroying it, how are they doing so without leaving a trace? The leading suspect is a slow internal process. As a star like our sun spins, its interior is not a uniform, static ball. Deep beneath the visible surface, currents of hot plasma rise, cool, and sink back down in a vast, churning conveyor belt known as convection. For most of a star's life, this churning is confined to the outer layers, but in a star's earliest youth, this convective zone may plunge all the way down to the searing hot core. At these depths, the temperature is sufficient to trigger nuclear reactions that destroy lithium, fusing it into heavier elements. The star, in its infancy, effectively burns its own primordial lithium fuel. This would explain the depletion, but it creates another puzzle. Our best models of stellar physics suggest this deep mixing should not be quite so efficient. The process seems to be far more effective in these cluster stars than in similar, isolated stars in the galactic field. This points to a hidden variable, something about the cluster environment itself that amplifies the destruction. Could the dense stellar neighborhood play a role? Perhaps the gentle gravitational tugs from thousands of stellar neighbors subtly alter a star's internal rotation or structure, stirring its interior just enough to send the lithium down to its doom. Or maybe the very fact that these stars were born together in a frantic burst of creation means they all share a unique internal dynamic, a faster spin or a different turbulence that primes them for lithium destruction from birth. The missing lithium is more than a chemical curiosity. It is a tiny, crucial clue that the simplest models of stars are incomplete, and that the crowded, ancient cities of the cosmos breed stars with profoundly different inner lives than the solitary suns we know best. Our own galaxy's stellar streams are not unique. Far beyond the Milky Way, wrapped around our nearest galactic neighbor Andromeda, astronomers have mapped colossal rivers of starlight that tell the same tale of disruption on a grand scale. These are the globular cluster streams of other galaxies, and they reveal that the process of cluster destruction and galactic cannibalism is a universal rule. Seeing these structures in another galaxy provides a crucial, wider-angle view. It allows us to study the life cycle of clusters from a distance, free from the embedded perspective we have within our own Milky Way. The observations are stunning. Long, faint filaments of stars curve around Andromeda's halo, each one the ghostly signature of a globular cluster that was torn apart by the larger galaxy's immense gravity. One particularly striking stream, dubbed the Giant Stellar Stream, is a colossal arc of stars stretching across tens of thousands of light years. Its origin is traced back to a dwarf galaxy that Andromeda is actively consuming, a process that is also stripping away and stretching the victim's own native star clusters into these luminous trails. It is a real-time demonstration of hierarchical galaxy formation, the idea that large galaxies are built by digesting smaller ones, and their clusters are torn apart in the process. This external view confirms something profound. The dissolution of star clusters is not a local anomaly or a rare event. It is a fundamental, ongoing process that shapes the halos of all large galaxies. By comparing the number, length, and brightness of these streams in different galaxies, astronomers can even begin to reconstruct a galactic diet history, estimating how many clusters and dwarf galaxies a galaxy like Andromeda has consumed over its lifetime. These faraway rivers of stars are more than just beautiful curiosities. They are the ultimate proof that the violent dynamics we witness in our own backyard are the standard rhythm of the cosmos, a relentless cycle of creation and destruction that weaves the very fabric of the universe on the largest scales. Even the closest stellar companions are subject to the brutal laws of a crowd. While we often picture stars as solitary suns, many are born in pairs, gravitationally bound for life. Yet when we census these binary stars across different clusters, we find a bewildering inconsistency. The fraction of stars living in pairs varies wildly from one cluster to the next, with some swarms hosting a thriving community of binaries and others appearing almost entirely single. This is not a random quirk of nature. The number of stellar couples is a direct barometer of a cluster's past violence, a fossil record of its gravitational history. In a young, loose open cluster, the stellar population is often rich with binaries, reflecting the conditions of their birth. But venture into an ancient, dense globular cluster, and the landscape of companionship is starkly different. The tightly packed core is a gravitational war zone where close encounters are a constant threat. When two single stars, or a binary and a single star, swing too near one another, the resulting gravitational chaos can tear a stable pair apart, flinging the stars away on separate paths. Alternatively, the encounter can forge a new, tighter binary in a process called exchange, where a more massive star kicks out the original partner and takes its place. It is a celestial partner-swapping dance, dictated purely by gravity and mass. Imagine a crowded, bustling party where conversations are constantly being interrupted and reformed, with louder voices eventually pairing up and quieter guests being left to drift alone. This relentless dynamical processing efficiently destroys the wide, fragile binaries and creates a few exceptionally tight pairs in the core. The cluster's age is the other critical factor. Billions of years of these stellar interactions act like a slow eraser, systematically dismantling the binary population. An old cluster has simply had more time to be stripped of its original couples. The consequence of this binary fraction is profound. These stellar pairs act as gravitational energy reservoirs. When they are plentiful, they can absorb the kinetic energy of passing stars through their complex orbital dances, effectively acting as a shock absorber that helps stabilize the entire cluster against catastrophic core collapse. A cluster rich in binaries can live a longer, more settled life, but a cluster that has been stripped of its pairs is far more volatile, its stars moving on simpler, more dangerous paths that can lead to rapid collapse or disintegration. The simple count of stellar couples tells a story of survival, destruction, and the invisible gravitational battles that define a star cluster's very essence. The hunt for these gravitational monsters hinges on a cosmic gap in our understanding. We have found stellar mass black holes, the remnants of collapsed stars, and we have found supermassive black holes, the leviathans that rule galactic centers. But the space between them, the realm of intermediate mass black holes, has remained a ghostly void. These are the missing links, with masses ranging from a few hundred to a few 100,000 suns, and their confirmed existence would rewrite the story of how the largest black holes in the universe are born. Star clusters, with their dense stellar nurseries, are the perfect places to look for them. The evidence so far is maddeningly indirect, yet deeply compelling. In several clusters, astronomers have tracked the motions of stars whipping around an invisible, monstrous mass at the core. These stars are not just drifting. They are caught in a frenzied dance, orbiting a point of seemingly empty space with velocities that betray the presence of something incredibly heavy and incredibly small. It is like watching leaves caught in a whirlpool, spinning faster and faster as they approach the unseen drain. These stellar motions are the primary clue, but they are not definitive proof. Skeptics argue that a tight knot of stellar mass black holes or neutron stars could mimic the same gravitational pull, so the search has expanded to other wavelengths, hunting for the black hole's voice. The latest tantalizing evidence comes from radio and X-ray observatories. In a handful of clusters, scientists have detected faint, flickering point sources of radio waves and X-rays emanating from the precise location of the suspected intermediate mass black hole. This emission is the signature of a cosmic feast. When a black hole actively pulls in gas, the material does not fall silently. It spirals into an accretion disk, heating to millions of degrees and glowing in high-energy X-rays before vanishing across the event horizon. Occasionally, it can also power narrow, ultra-fast jets of material that shoot out into space, emitting strong radio signals. Finding this combination, a concentrated gravitational anchor paired with the high-energy glow of accretion, is the closest we have come to a smoking gun. One of the most promising candidates resides in a cluster called 1060. Here, a steady radio source coincides perfectly with the dynamical center, and the surrounding stars move as if tugged by a black hole weighing several thousand solar masses. Each new observation brings us closer to confirming that these middleweight monsters are not just theoretical phantoms, but real engines of gravity hiding within the oldest stellar cities in the universe, waiting for their moment to be seen. Even the most brilliant stellar giants can vanish behind a veil of their own making. Deep within the nurseries of young, massive clusters, a hidden population of stars burns with a ferocious intensity, yet remains completely invisible to our optical telescopes. These are the dust-enshrouded massive stars, stellar behemoths so thoroughly cloaked in thick cocoons of cosmic soot that their dazzling light is absorbed and transformed, only re-emitted as a faint, warm glow in the infrared part of the spectrum. We are essentially blind to their true presence until we look with the right eyes. How does a star, capable of outshining thousands of suns, simply disappear? The answer lies in its own violent birth and turbulent youth. These stars form from the densest, most gas-rich regions of a cluster. As they ignite their nuclear furnaces, their powerful radiation and stellar winds collide with the vast reservoir of cold gas and dust from which they were born. This surrounding material, instead of being blown away, gets compressed into a nearly opaque shroud, a dense shell of microscopic dust grains that acts like a stellar burqa. The star's intense ultraviolet and visible light slams into this dusty cocoon, where it is absorbed. The dust grains heat up to a few hundred degrees, and they re-radiate that absorbed energy at much longer infrared wavelengths. To an optical telescope, the star is a ghost, but to an infrared observatory, it shines as a brilliant beacon, a hidden titan revealed only by its thermal warmth. This discovery forces a complete revision of our stellar censuses. We thought we had a good count of the most massive stars in these clusters, the primary drivers of their evolution. But the existence of this hidden population means we have been missing a significant fraction of the most influential members. These shrouded giants are the primary sources of heavy elements and the eventual progenitors of the most powerful supernova. Their hidden lives, playing out behind curtains of dust, mean that the true power and energy output of a young star cluster has been vastly underestimated. It is a cosmic reminder that what we see is only a fraction of what is truly there, and that the universe's most dramatic actors often perform behind the scenes. A star cluster's long orbit around the galaxy is not a serene cruise through empty space. It is a journey through a treacherous gravitational landscape, one that can deliver a sudden and violent jolt. When a cluster plunges through the dense plane of the galactic disk or swings perilously close to the immense bulge at the galaxy's core, it experiences a phenomenon known as tidal shock. This is not the slow, steady pull that creates tidal tails, but a sudden, intense gravitational slap. The cluster, as a whole, feels a dramatically stronger pull on the side facing the galaxy's mass than on the side facing away. This difference in force acts like a sudden explosion of energy inside the cluster, violently stirring up the orbits of its constituent stars. Picture a calm, placid pond. Now throw a large rock into its center. The resulting splash and the radiating waves are a shock that disrupts the water's serene surface. A tidal shock does the same to a star cluster, sending a gravitational wave of energy through its stellar population. This injection of energy has a direct and destructive effect. It heats the cluster. In this context, heat does not mean temperature, but motion. The stars gain random velocity, their orbits becoming more energetic and chaotic. This causes the entire cluster to puff up, expanding in size as the stars are driven to higher, wider orbits. The most vulnerable stars, those on the outermost edges with the weakest gravitational bond, receive the biggest kick. This sudden heating can be enough to give them the escape velocity they need to break free entirely, flinging them into the galactic halo ahead of schedule. It is a rapid and brutal acceleration of the cluster's evaporation process. Each close passage past a galactic landmark acts like a hammer blow, shaking the cluster's foundation and stripping away its outer layers. A cluster on a highly elliptical orbit, one that regularly dives through the galactic disk and sweeps near the bulge, will experience these shocks repeatedly over its lifetime. With each shock, it loses a little more of itself, its stellar population thinning out, its gravity weakening, making it even more susceptible to the next encounter. This process is a key driver in the life cycle of these celestial cities, determining not just how they live, but how quickly they die, their longevity written in the perilous path they trace around their galactic home. The violence of a galaxy's birth is permanently recorded in its collection of star clusters. While two galaxies might look nearly identical today, with the same mass and shape. One could be surrounded by a glittering swarm of thousands of globular clusters, while the other possesses only a few hundred. This bizarre disparity is known as the specific frequency anomaly, and it reveals that a galaxy's history is anything but simple. Why would two cosmic cities of the same size have such drastically different numbers of ancient stellar families? The answer is not in their present state, but in the chaotic collisions that built them. A galaxy that formed slowly and peacefully from a single, collapsing cloud of gas would naturally gather only a modest population of globular clusters native to its own halo. But a galaxy that grew through a series of violent, major mergers tells a different story entirely. Each time two sizable galaxies collide, they do not just combine their stars. They also pool their entire systems of globular clusters. It is a cosmic corporate merger, where the new, larger company inherits all the assets, all the employees, from both of the original firms. A galaxy like our Milky Way, with a few hundred clusters, likely had a relatively quiet upbringing, but a giant elliptical galaxy at the heart of a dense cluster, like M87, which is surrounded by thousands of globulars, is a different beast. It is a galactic empire built through conquest, a dominant giant that has absorbed countless smaller galaxies over billions of years, each one contributing its own clusters to the victor's glittering trophy case. This means the number of globular clusters a galaxy possesses is not a measure of its current size, but a tally of its past victories, a count of the stellar cities it has consumed on its journey to becoming a cosmic titan. A final invisible fire burns within the oldest star clusters. When astronomers gaze upon the serene, red glow of giant elliptical galaxies, they detect a persistent and puzzling signal, an excess of far ultraviolet radiation that should not exist. These galaxies are cosmic retirement homes, filled with ancient, cool stars that emit most of their light in red and infrared wavelengths. They should be ultraviolet deserts, yet they shine with an eerie, high-energy light. The source of this mysterious energy was traced not to the galaxy at large, but to its vast populations of globular clusters. Within these ancient swarms, a specific and short-lived class of stars is responsible, the extreme horizontal branch stars. These are not massive, young stars, but the exposed, superheated cores of ancient sun-like stars that have been stripped nearly bare. An ordinary horizontal branch star burns helium in its core and is enveloped by a thin blanket of hydrogen. But an extreme horizontal branch star has lost almost all of that protective hydrogen blanket. With its hot, helium-burning core directly exposed, it radiates at ferocious temperatures, shining with an intense, ultraviolet light that belies its advanced age. It is the stellar equivalent of an ember that, instead of cooling, suddenly flares white-hot. This creates a profound paradox within the peaceful-looking elliptical galaxy. The collective ultraviolet output from thousands of these tiny, hot embers, scattered across countless globular clusters, combines to drench the entire galaxy in a faint, ghostly ultraviolet glow. The great mystery is not their heat, but their origin. Why do some clusters produce so many of these radically stripped stars, while others, seemingly identical, produce almost none? The answer appears to lie in the complex social dynamics of the cluster itself. A star's journey to becoming an extreme horizontal branch star is one of dramatic loss. It must shed its outer layers with extraordinary efficiency. In the dense core of a globular cluster, close encounters with other stars, or the vampiric influence of a binary companion, can efficiently peel away a star's hydrogen envelope, leaving behind a naked, blazing core. The specific recipe of stellar interactions, spin, and chemical composition within each individual cluster dictates whether it will become a factory for these ultraviolet powerhouses. This far ultraviolet excess is more than a simple anomaly. It is the collective scream of a billion dying stars, a testament to the violent and intimate histories written in the crowded stellar cities, reminding us that even in the reddest and oldest corners of the universe, a secret, energetic fire still burns. This journey through 50 strange discoveries reveals a cosmos far wilder than we ever dreamed. We have witnessed stellar cannibals, ancient planetary survivors, and stars that cheat death. We have found clusters with two hearts, stars that do not belong, and phantom streams that are the ghosts of devoured galaxies. Each of these findings peels back a layer of what we thought we knew, forcing us to rewrite the fundamental rules of astrophysics. The serene star clusters we see as faint smudges of light are not simple fossils. They are dynamic, violent, and endlessly surprising ecosystems, each one a cosmic storybook filled with tales of creation, destruction, and rebirth. They challenge our definitions of planets, stars, and even galaxies themselves. So the next time you gaze up at a dark, clear sky and spot one of those faint, glittering swarms, remember the truth. You are not just looking at a pretty collection of stars. You are seeing a cosmic laboratory, a turbulent city of suns where the laws of physics are tested to their absolute limits. Let that knowledge fill you with a new and profound sense of wonder, and we would love to hear from you. What is your favorite cosmic mystery? Share your own thoughts and questions in the comments below.